Hi, welcome to the Signal Path. This episode is all about nonlinearity and distortion. I want to take a look at what the causes and the source of nonlinearity is in amplifiers. So first I'm going to look at it mathematically, find out what a mathematical representation is of a circuit that's nonlinear. Then we're going to build that circuit and actually measure it here in the lab and see nonlinearity effects right in front of us. So we can build a circuit where we can apply a nonlinear component to it and then remove the nonlinear component, and then we can see the huge difference between the spectral content of those two signals. Now what I can do here that will be beneficial is that we can look at nonlinearity both as an equation in the time domain and in the spectral domain all at the same time. So that gives us a very powerful visual aid to take a look and see what each effect is clearly represented in each domain, because it's important to be able to think both in the time domain and in the frequency domain as a circuit designer, because then you can relate how each effect manifests itself depending on how the circuit is supposed to operate in real life. And then we'll also talk about some of the bad things nonlinear circuits can do to your signal and some of the good things nonlinear circuits can do to your signal, because both of them are used widely in all kind of applications. So let's get started. So let's start with something really simple. Let's start with a circuit like this that we know is completely linear. We have an input here Vn, and we have two resistors of equal value R and R, and then we have an output on the other side. So this is just a resistive divider that divides the signal V out with respect to Vn. So if we assume that the input is a simple sinusoid with a single frequency at its input, so A sine of omega t, then the output will just be half of A sine of omega t. And the reason why this is a one-to-one linear relationship is because the current versus voltage relationship of a resistor is linear. It's Ohm's law. So the current times the resistance is the voltage, which is a linear equation. But this is not always the case, because these, although resistors are linear, many other circuit elements such as transistors and diodes and so on are not linear circuit elements, and they can add nonlinearity. So let's look at this most simple case of building a nonlinear circuit so that we can actually build in the lab and start measuring. So let's look at this circuit now. Now imagine you have exactly the same circuit we had at the top, but now we add a diode at the output of the circuit. So we have the same resistor divider and a diode. Now the current in the diode is given by an exponential function. So it's Is, which is related to the area of the diode, then e to the V out over Vt. So you can see when V out gets divided by Vt, and if V out is twice Vt, then it's e to the 2, and if V out is 4 times Vt, then it's e to the 4. So you have an exponential rise, an exponential relationship between V out and the current that is going through the diode. Now you can use a series expansion equation, such as this one, to describe the exponential function. In that case, we have the following equation. I'm actually missing Is in the front here, so imagine there is an Is being multiplied here. So Is times the sum of from 0 to infinity of V out over Vk to the power of k divided by k factorial. Now, if we again imagine that V out had a component of a sine of omega t in it, like it was written up here. So if you imagine that V out had a sinusoid component in it, and then we look at this equation again and plug in a sinusoid of a single frequency in the place of V out and expand it, we will get the following. We will get A times, which is A some factor, times sine of omega t, and then B some other factor, times sine of 2 omega t, plus C times 3 omega t, and so on and on all the way to infinity. So this tells us something very important. Unlike the circuit above, where the output was simply had only one frequency content, the same frequency content as the input at the frequency of omega, the circuit with the diode, because of the nonlinear relationship between the I and the V of the diode, has frequency components not only at omega, the original frequency, but also at 2 omega, 3 omega, 4 omega, and so on. And the reason is because when you square a sinusoid term, for example, let's say V out is sine of omega t to the power of 2, then that will give you sine of 2 omega t. It will have a component of at twice the frequency. You can convince yourself of that, and you should definitely do this. Go to Wolfram Alpha. Let me show you in here, for example. Go to Wolfram Alpha and type for yourself something that you want to see the series expansion for. So I can, for example, type here sine of x to the power of 2, and then you will see that it will compute for me the value for that. And if I come over here, and you can see that sine squared of x has a component of sine of 2x in it, which is exactly what I was saying before. So when you take a component of sine and then square it in this equation, which is a series expansion for the exponential function, you are going to get all the multiplied factors of your original frequency. So what does that mean after all this math? Well, that means that here's the spectral content of my input signal. I put in a single tone at the frequency of f0 into my circuit. If it's a perfectly linear circuit, I expect the exact same spectral content, only frequency f0 to come out just like it would here. In this case, it would be half the amplitude. So this is not an amplifier, it's an attenuator, but it doesn't matter because it's completely linear. So I put in f0, I get out f0. But if the circuit is not linear, I put in f0 like so, and I not only get f0, but I also get 2f0, 3f0, 4f0, all the way to infinity, and the amplitude typically start to go down. So now this is not a good thing, because this means that your spectrum is now occupied a whole bunch of other tones that wasn't available when you put your input signal in. So depending on what you are doing, this could be very bad. Let's say you're listening to some music, and then you put in a clean spectral content of the song you're listening to, and it goes through a non-linear amplifier, and then it comes out and it sounds absolutely horrible. The reason it sounds bad is because your amplifier was non-linear, so then all these extra tones were created and they get summed up and they get mixed together, and your spectrum becomes just a mess, and you can hear that as distortion in the music you're listening to. So for us, we're going to build this circuit, measure it both in the time domain and in the spectrum domain, so then we get to see exactly that it is indeed you put in a single tone and you get a single tone out, and then we will build this circuit and we'll put in a single tone and we'll see the mess that comes out, and then we'll talk a little bit more about the results. So I'm going to set that up and we'll be right back. So let me explain what the setup looks like. I have an oscilloscope, the Tektronix TDS210, so I'm going to look at the signal in the time domain using this instrument. I also have an Agilent 8595E, so I'm going to look at the spectral content of the signal on this instrument. Now some of you may ask, well, why not just use the FFT function built into here? Well, there are two reasons. First of all, in this one, once I take the FFT, the screen becomes too cluttered with all the information because the screen is only black and white. But the main reason is that the dynamic range you get from an oscilloscope when you perform spectral calculation is nothing that even comes close to the spectral content that you can get, the dynamic range you can get from a spectrum analyzer. This is because this is mathematically computed using a low resolution A to D converter, whereas this guy has a very high resolution A to D converter and actually down converts chunks of frequency and gives you a very high dynamic range. So nothing can beat a good spectrum analyzer when it comes to spectral information. So I'm going to use this guy to look at the spectrum. I'm going to use an HB33120A arbitrary waveform generator to just generate a simple sinusoid. You can do that with any function generator that can give you a single tone sinusoid. And I'm using a power supply here, the Rigo DP1308A, which I've reviewed before, to power a little amplifier that's on the board, and I'll talk about the circuit in a moment. So we're going to use all of these guys together, and I've built the circuit right here that I showed the schematic for. And everything's hooked up and connected, and we're going to measure it. The only one thing that I've done is that here, instead of connecting my signal source directly to VN, I've placed an amplifier in the front that has a gain of 1. This is just a buffer, so for all of our purposes, we're going to assume the amplifier in the front has basically is completely linear, and we're only concentrating on this circuit and concentrating on this circuit. So that's the reason why I need the power supply, is because there is a little amplifier in the front. So we're going to ignore that, but you will see it in the circuit. So let's take a closer look at what we have. If I can position this camera. So here's our circuit. As I was saying before, here's a little amplifier. It's just an opamp in the front that's configured to have a gain of 1. And here's one of the resistor divider, here's the other resistor divider, and here's my diode that I had drawn in the schematic. So right now the diode is not connected to the resistor divider. So I can look at the output of the resistor divider directly and put a single sinusoid input using these two connectors. So that so the signal comes in, goes through my little op-amp that has a gain of 1, goes through the resistor divider and comes right out. And right now it is not connected to the diode. So we can take a look and see what that looks like. Alright, so the frequency that I'm using is 1.5 megahertz, and I'm using a 2 volt peak to peak sinusoid signal to apply to this circuit. So the signal is coming in. I'm going to take the 2 channels of my oscilloscope, I'm going to connect one of them to the input. Like that. And I'm going to connect the other one to the output. Like so. There we go. Turn the power supply on. Alright, so let's look at the signal and the time domain first. So you can see that the input signal is at the bottom and the output signal is at the top. So the input signal has twice the amplitude of the output signal because the 2 resistors are equal, and the gain of the circuit is 1/2. So the output is half the input. So if I go into the measurement menu, I can see that my channel 1 peak to peak is 960 millivolts, so about 1 volt peak to peak, and the output is about 1.8, so it's about 2 volt. There's some attenuations and so on in the probe, so we can ignore that for now. So okay, I repositioned the camera so you can see both signals at the same time. So here's the input, here's the output. I'm also going to now connect the spectrum analyzer and directly look at the output signal. And here we go. There it is. So we've already seen the signal on the oscilloscope. Let's take a closer look at the signal on the spectrum analyzer. So here's our main tone. That's the signal I'm putting in. So if I put a marker on there, you can see that it is 1.54 megahertz, very close to 1 megahertz, 1.5 megahertz, just like the signal generator is creating. So here you can see that the main tone is so much larger than this tone here, and this tone is in fact at exactly 3 times the frequency of the first tone. So if I put a marker on that, you can see that it's at 4.5 megahertz, which is 3 times the frequency of the input signal. So this tells me that there is already a little bit of nonlinearity in the circuit, and that nonlinearity from the circuit comes from the op-amp, and also comes from the signal generator itself, because the signal generator cannot create a very, very clean signal. But remember, the distance between these 2 tones is enormous. Each of these divisions is 10 dB. So this guy is about 1, 2, 3, 4, about 40 dB less power in the third harmonic than it is in the first harmonic. Now this circuit doesn't have the diode connected to it, so it's extremely linear. So this circuit will work really well if you were passing, let's say, an audio signal through it, or some other signal that you wanted to attenuate. So now let's add a diode and see the effect of that. So I'm going to bring the camera here, and I'm going to take a wire, and I'm going to connect the output of the circuit to the diode like so. So now it is connected. So let's take a look first at what happened to the time domain signal. If you can tell, the signal, the output, doesn't look sinusoidal anymore. It's clipping at the bottom. And that makes sense, because the way I've connected the diode, when the signal goes below 0, sufficiently large enough, the diode's exponential current kicks in and clamps the output. So sometimes people use these diodes to clamp an output, make sure it doesn't get larger than a certain value. So I'm going to remove the jumper so you can see before and after live. So here's with the diode, here's without the diode. You can see how nice and sinusoidal the signal looks, and as soon as I add the diode, if I can plug it in again, you start getting the clamping like so. So here's with it and here's without it. So now that we know what it looks like, we can see the same effect in the frequency domain right in front of our eyes, and you can see all the harmonic generation like we were saying before. So I've disconnected the diode. Here's the signal. It's nice and clean. Oh, it's hard to focus this. And I'm going to plug in the diode, and look at that. Look at all those extra tones that weren't there before. So here's a fundamental tone, the frequency that we're actually interested in. Here's a second harmonic, third, fourth, fifth, sixth, all the way out. The span of this is from 0 Hz to 15 megahertz. So those harmonics will keep going, but they will get smaller and smaller as the frequency increases. So I can increase the frequency so we can see the harmonics, how much smaller they will get. So I'm stopping instead of 15, I'll stop at 30. So you can see a whole bunch of harmonics, and they get smaller and smaller, and the reason they get smaller is because of the bandwidth limitation of the system itself. So they slowly get smaller, and also as you square the sinusoid terms, the coefficients will get smaller. So you can see that all those harmonics are undesired. The only thing I wanted was the first harmonic. So here I'm removing the diode. See how all of them go away except the little one, the tiny one that we started with, and that's because of the, as I was saying, some of the nonlinearity of the signal source itself, so I can't really get rid of that. So you can see how much of a damage just this diode does to our signal. Like so. So let me go back to 15 megahertz again. We can see all of our tones. Now I'm going to do something interesting, and I'm going to add another diode to the circuit. And I'm going to add the other diode to the circuit in this way. Put this guy here. It's going to be hard to see. So here's the original circuit. This is the circuit that we built. Now I'm going to add another diode to it. And I'm going to add that diode here. Like so. So what that diode will do is that this diode was only turning on when the signal was on the positive side. So this is the opposite of what I had on the breadboard. But this guy will turn on when the signal swings up. Now this guy will turn on when the signal swings down. So it will clamp not only on the positive but also on the negative. And it has a very interesting effect. So let's look at that. So let me remove that so you can see it. So here's the original diode. I have another diode like this, and I'm going to plug this in the opposite orientation at the output. So let's look at the signal in the time domain. So as I was saying, and as we predicted, now the signal will be clamped not only at the top and also at the bottom. And we can see that here. You see at the bottom is clamped, and it's also clamped at the top. So I'm going to remove the diodes together. So here's a nice sinusoid, and here's a double clamped. And I'm going to remove one of the diodes. You can see it's now only clamped at the bottom. And when it was only clamped at the bottom, we already saw the spectrum. It looked like this. Like that. You can see first harmonic, second. So there's a big second harmonic sitting here, a big fourth harmonic sitting here, and a third harmonic that's in the middle. So I'm going to add the diode back in the circuit, and look at what happens to the spectrum. Now isn't that incredible? The second harmonic, the fourth harmonic, the sixth harmonic, and the eighth harmonic completely disappeared. They went away. So now this is my quiz for this tutorial. Tell me, why would the addition of the second diode eliminate so much of the second, fourth, basically all the even mode harmonics? Why are the even mode harmonics all gone? If you can explain that, post it either on the forum or in the comment section so everyone else can benefit from it as well. So what else can we do with this type of circuit? I mentioned that nonlinearity is a bad thing, but sometimes it can be a good thing also. So what can we do with this as an example? So let's say that I have a signal source that's 1.5 megahertz and I need 3 megahertz. Well, I can see that in this signal I have 1.5 megahertz and I also have 3 megahertz signal both present simultaneously. So if I could somehow filter the fundamental tone, I would be left with a signal that is stronger than all the other tones. So I would have a circuit that can triple my frequency. These type of circuits are built all the time. For example, a frequency doubler, frequency tripler, and so on. So if I build a proper filter here and a proper filter for the output, I can put in 1.5 megahertz and get 3 megahertz. So that would be, for example, one application of having a nonlinear circuit. And of course, the main application for having nonlinear circuit is to build mixers which do frequency translation. So I'm going to leave mixers for a different tutorial. Now what I'm going to do is I'm going to show you why this type of circuit is bad for wireless circuits. So I'm going to change the setup a little bit, then we'll talk about input compression, and we'll talk about the third order intercept point, and so on. So we learn how nonlinearity is actually measured besides just seeing it on the screen. So if you were to report the nonlinearity of a circuit, what is it that you have to report? So before we go on to the next experiment, I want to talk about some limitations of measuring distortion. So let's look at this, which is what I showed before. Imagine that we put in a signal of F0, and then we get all these harmonics, 2F0, 3F0, 4F0, which represent the nonlinearity of the circuit. You can calculate what is called a total harmonic distortion, which is the ratio of all the unwanted tones to the fundamental tone. So you can sometimes see total harmonic distortion represented in percentage, or you can see it as in dB. For example, I could say that the total harmonic distortion is minus 30 dB. Means that the power of all the unwanted tones is 30 dB less than the power of the tone that we want. That may sound like a lot, but 30 dB is actually only 6 bits. So it's actually only 5 bits, so it's not very much at all. But what if our amplifier had a bandwidth limitation on top of it? So this amplifier that I've drawn here, that's nonlinear, I'm assuming it has infinite bandwidth. But what if the bandwidth of the amplifier looks like this, and you want to measure its distortion near the edge of its bandwidth? So let's think about what would happen. Let's put some numbers on this just for the sake of comparison. Let's imagine the bandwidth is, for example, 10 megahertz. And I want to find out the linearity at 9 megahertz. So if I put in 9 megahertz, my second harmonic is at 18 megahertz, and the third one is at 27 megahertz. The 27 megahertz and 18 megahertz are all way above the 10 megahertz bandwidth of the signal. So they're going to be attenuated, they're going to look very small. So you're going to measure your total harmonic distortion, and you're going to realize that, hey, it looks really, really good. But in reality, you're actually making an error because you're not counting for the fact that the filter behavior of the amplifier itself is attenuating your harmonics and making you think that the signal is much more linear than it actually is. If this tone was all the way here, then the second harmonic would still be within the bandwidth, then you will see its actual value, then it may be much larger. So in order to avoid that, how people measure total harmonic distortion, or for wireless terms, how they measure the third order intercept point, which I'll talk a little bit about, is that they put in two tones at the same time instead of one. So here's an example of a wireless receiver. So I say wireless because it has a bandpass response. So for example, let's imagine this is a Wi-Fi signal around 2.4 gigahertz. And this is your channel, meaning that you're saying I'm going to occupy, let's say, channel 11. And channel 11 only gives you 100 megahertz, so your signal has to stay within 100 megahertz of your center channel. So how can you measure the total harmonic distortion, or in this case the IP3? You would put in one tone at F0, then you put in another tone at F1, and the distance between those two tones in frequency we call delta F. Then if you go through the math, which I encourage you to take a look at, these tones mix all together, and the non-ideal harmonics all get mixed up together, and they show up as sidebands on the both sides of your main tones that you put in. So you will get a little bit of tone here, that's F1 plus delta F, and you get a little bit here, F1 minus delta F, and then F1 minus 2 delta F, and then 2 delta F on that side, and so on and on. So ideally, you put in two tones, you don't want any of these, but these guys creep in because of the nonlinearity. Now in a wireless circuit system, this is very important because this means that by generating these tones, you could actually be occupying your neighboring channels that don't belong to you. So there is another guy sitting here with his own two tones and a different channel trying to send and receive data, but if the harmonics of your signal occupy his channel, now you're fighting him for his signal. So then the receiver is going to be confused. It doesn't know if it's listening to your harmonics or if it's listening to the signal the actual user is sending. So if you don't meet the requirements and make sure that your harmonics, your nonlinearity is low enough, your circuit's not going to pass the mass, may not pass the FCC, and you wouldn't be able to put it into the market. So this is a very, very important test. And then people measure how fast these grow and then where they meet. And I recommend that you guys go and read that because it becomes a little more technical and it would be very boring for me to go through it. But if you have a bandpass circuit like this, you cannot measure its linearity by putting a tone, single tone like that, because the harmonics would be way out of band. Here, a 2.4 gigahertz signal, its harmonic would be at 4.8, it's way out there and you would never see it. So that's why people put in two tones. So what I've done here is I have done exactly that. I have taken my signal from my original Agilent signal generator, and I have another arbitrary waveform generator here. So I'm taking the output of this and I'm combining those two outputs together in this combiner here, and then feeding the combined signal back into our circuit, and then we will see exactly what that does. So I have done, basically the setup is exactly the same. The only difference, it has now two inputs like this. It has a tone at F1 and a tone at F0 and a tone at F1. This guy is at 1.5 megahertz. This guy is at 1.6 megahertz. So they're 100 kilohertz apart, and I'm applying them simultaneously. So let's look at what that looks like in the time domain. Now this is what that looks like. It doesn't really tell us much, and this is why it's so important to be able to think both in the time domain and in the frequency domain, because when you are faced with a signal like this, it doesn't really tell you much. I mean, I could do this and this is what you're going to see. Kind of makes sense because you know there is two signals, both sinusoid, and the frequency is a little bit different, so they combine together linearly and they create what's called a beat frequency, which is a frequency in which they destructively combine, and then a little bit later they constructively combine. So if I go on a time scale like this and I stop it, you can actually see the beat frequency. The beat frequency will be the distance between these two guys, and it's actually going to be the delta F, which is 100 kilohertz. So here's the signal at the input, here's the signal at the output. Right now the diodes are not connected, so this is a completely linear circuit for us. So yeah, we can look at the spectrum, and here's the spectrum, and it looks good. Here's my 1.5 megahertz signal, here's my 1.6 megahertz signal, and you can see on both sides there is absolutely nothing because the circuit is completely linear and we don't have any distortion at all. So I'm going to run the oscilloscope again, and let's come back here and look at the oscilloscope. I just want to show you how it's impossible to tell that it's nonlinear in a situation like this. So this is what it looks like. I'm going to add the diode, and this is what it looks like now. Well, you can kind of see that it's clipping, but the only reason you can see it's clipping is because I'm seriously applying some nonlinearity to it. In reality, you wouldn't be able to see this at all. So now let's look at the spectrum. So I'm going to disconnect the diode. So here's the spectrum, okay, like so, and I'm going to add the diode and watch for the intermodulation products, which are the products that will show up on either side of our signal. So here we go. Connected, and here's all the nonlinearities. So this nonlinearity and that nonlinearity on each side, and there is even more terms. This is the third order intermodulation product on each side, and these are the fundamentals. These guys can cause some serious problem in wireless circuits, and they're essentially not allowed to. If your circuit was this bad, forget it. It wouldn't work at all. So this is the importance of being able to relate the math to the time domain and then to the frequency domain. And that way we can have a good idea of how each of these phenomena look in each of these domains. And I strongly recommend that you guys go ahead and study this material. A lot of books and papers and so on is available for you to learn about this. You can even find a majority of this information on Wikipedia. But now we have a good understanding of, you can actually go ahead and build this circuit in the lab. All I needed was some signal generators and some resistors and diodes, and of course, well, the equipment. But in terms of circuit elements, we could demonstrate all of these nonlinearity effects and even a two-tone test by using simply diodes and resistors. And don't forget to solve the puzzle of why the two diodes eliminated the second order harmonic in our first test. Just one other minor note. I mentioned that I have an op-amp in the front, and I'm biasing the op-amp using plus and minus 15 volts, which is much higher than the input signal that I'm applying to it, and the op-amp has a gain of 1. So this way I can make sure that my op-amp is not adding any nonlinearity. But I could actually remove the diode and then lower the power supply of the op-amp, and then the op-amp will start generating nonlinearity. And I think that might be interesting, so we can take a look at it. So let me go, so it's right now it's at plus and minus 15 volts, so I'm going to disconnect the diode. So let's take a look at the signal. See, looks good, two tones, completely linear. So now I'm going to reduce the power supply of the op-amp. I'm going to go down to, let's say, from 15 volts to 3 volts. And let's see if this gets more nonlinear. So here we go. First one, 3 volts and minus 3 volts. There we go. Now you can see some nonlinearity starting to kick in. Why does this happen? This happens because the op-amp now is running from plus and minus 3 volts, but it's supposed to put an output of 2 volt peak to peak, and there is another one from the other tone, so it has to put out almost twice as much as that. And it can't do that because it doesn't have a supply that's large enough. So now I'm going to make, if I reduce the supply even further, instead of plus and minus 3 volts, I'll make it plus and minus 2 volts, and you will see even more nonlinearity. Here we go, and we go back. Well, I hope you guys enjoyed this episode. There's a lot of theory in there, so I'm hoping that I hit a good balance between practical aspects and theoretical aspects of nonlinearity and distortion. This is something that you should definitely study more, especially if you're in this field, because if you cannot make a linear circuit and if you cannot take advantage of nonlinear circuits in the right way, then you wouldn't be a very good circuit designer. So I have a lot of ideas. I just don't have enough time to make all the videos that you guys are asking for, but your support is always appreciated, and I can see that you guys are enjoying these videos, and that's a good reward in itself. So next time I think I'm going to do a teardown video. Basically any of the equipment that you see here I can open and show you the insides and talk about exactly how they work. And I can also talk about how I fixed them, because most of these equipments I've bought while they were broken, and I've repaired them and I'm able to use them. So I can talk a little bit about what was wrong with each one, how I found out what was wrong with it. And sometimes it was very easy to find, sometimes it took a very long time. So we can talk about that too. Leave us comments and rate the videos as you see fit, and then hopefully we can make more of these videos. Thank you.